Thank you. Good afternoon, everyone. My talk is on integrated sensing and communication. So, I'll briefly speak about the fundamentals and recent advances. So, this is the outline of my talk. I'll give a brief motivation to the introduction and to spectrum sharing, followed by the two potential solutions, that is communication and radar coexistence, and integrated sensing and communication. Followed by, the first three topics are basically I'll speak about the fundamentals, and then I'll speak about the recent work, that is the rate analysis of NOMA assisted ISAC. And if time permits, we'll talk about the potential problems in ISAC. Yeah. So we know that the rapid development of wireless communication systems in 5G networks and beyond. The aim is to deliver high data rates and higher quality of service. So it has been reported that by 2030, the number of connected devices will exceed 29 billion. So due to this, there will be exponential growth of wireless communication services and devices. So that rapidly increase in the application using the radio frequency spectrum. So that means that there's an overlap of wireless communication networks with conventional radar systems. So due to this, there are two problems. So one is the frequency spectrum is becoming increasingly congested, and with that, electromagnetic spectrum resources are also becoming limited. So now the question is how to overcome the profusion of connected devices and utilize the radio resource efficiently. So the network providers aspire for opportunities to reuse spectrum allocated for radar due to the large spectrum availability at radar frequencies. So, which means that spectrum sharing could be one of the potential solutions to overcome the spectrum congestion, where the aim is to enable radar and communication systems to utilize the radio resource efficiently. So basically, I'll speak about two solutions. So the first thing is, when we have fixed separated spectrum, which means that the spectrum are dedicated to specific communication and radar applications. So other one is dynamic shared spectrum, where the spectrum are available for both communication and radar purposes simultaneously. So when we talk about communication and radar spectrum sharing, the objective is that the communication system and the radar system are coexistent. So which means that we need to design efficient interference management technique. That's one of the thing. And why do we need to have this coexistence of communication and radar? So that is to achieve smart connectivity of everything. And also the other purpose is we want this wireless devices need to be integrated with the ability of radar sensing. So environmental monitoring, and also to satisfy the increasing demands for ubiquitous sensing and communications. So now the two potential research directions to achieve spectrum sharing are the following. So first thing is communication and radar coexistence. I'll briefly talk about the system model. And then the integrated sensing and communication. Again, I'll speak about the design configurations and the sensing configurations in an ISAC system. And we'll talk about the trade-offs between these two systems. So when we say communication and radar coexistence, that means there is dedicated radar transmitter and receiver, which exists along with the dedicated communication transmitter and receiver. So that means that there is cross interferences between them. Now in integrated sensing and communication, it's basically a unified framework integrating the radar and communication as a dual function RF system. So using this, the cross interferences can be overcome. So let us see individually. So this is just one system model where there is a communication, there's a base station, and these are the users, and we have the radar transmitter, and which also has the echo that will be heard from the target. So both systems use the same bandwidth. So each system receives its own signal. So that means that the communication transmits the information to the users, while the users will receive the interference from the radar. So similarly, the radar, when it is transmitting the signal to the target, so it receives an interference from the communication. So because of this, there will be interference between them. So the objective is to develop efficient interference management techniques. So basically, so when we say coexistence of communication radar, they are separated in their location with cross interference between them. Now, if you look into this system, so this is basically taken from one of these papers where they have considered a simple CISO system where the target is located at a range R and there is a delay which is equal to twice R divided by C, and it is assumed that the target is moving with the radial velocity V and the corresponding Doppler frequency FC. Now, for this system, if you look at the received baseband signal at the radar, so let us not get into the details of this equations. The first part is the radar component, and the second part is the interference from the communication, and the third part is the noise. Okay, and the other coefficients what we see here is this is the radar cross section coefficient. This is the propagation delay of the radar, and similarly there is a propagation delay from the communication transmitter to the radar receiver. Now, after passing this through a match filter, it's more easy to realize match to the radar waveform and then sampled at the radar pulse rate. We can see that this component is the radar signal, then the communication signal, then this noise. Now, similarly, if we look at the received signal at the communication user, the first component is the communication signal, then we have the interference from the radar, and then we have noise. So similar to what we saw in the radar, if we pass this through the match filter, so we have this signal component of communication and then the radar plus noise. Now, when we have such interference, now our objective is to design either a communication centric system or a radar centric system. So now if we talk about communication centric system, so our objective would be to improve or maximize the capacity given a service constraint on the radar. That means it needs to maximize the capacity of the communication user such that the power coefficients of the radar and the communication signal should be within the range of 0 to 1. Now the constraint, the SINR of the radar. Now similarly, if we look at the radar centric, now our objective is to design to maximize the SINR of the radar waveform given the constraint that the power coefficients is same, but now the constraint is on the communication user. That means the communication capacity should be greater than certain threshold.
What is sigma here in the equation? One is that the noise.
Sigma. This one, yeah, this is the noise component. So this is basically communication signal power, radar power plus noise. And similarly, when you look at the SINR of the radar, we have the radar signal power plus the interference is from the communication, and then we have noise. Yeah, so now if we look at the integrated sensing and communication, I'll compare the things later. Now if you look at the integrated sensing and communication, so we have a transceiver which is basically a full duplex system. Now our objective is to unify this single transceiver for the purpose of radar and communication. Now there is no separated or there is no dedicated transmitter and receiver for the radar or the dedicated and transmitter and receiver for the communication. So this it's a full duplex system where the communication users are coexisting along with the targets. Now our objective is to what? Our objective is to probably to design a waveform such that we can serve both the communication user and also the targets. Yeah. So radar, when we say radar sensing, it could be detection of these targets, or it could be estimation of some parameters like velocity or the to determine activities in an indoor environment or human gesture recognition. These are some of the examples of radar sensing. Now, when we talk about ISAC, there are three types of configuration. So in the first figure, if you see, there is a base station, there is a receiver and a target. Okay. Now, where are we going to sense the target? If we are doing it, the base station, which is also having the capability of transmitting the signal, that means transmission and reception is done at the same point, then it is called as monostatic sensing. If we are doing sensing at a separated location or a discrete place, then it is called as bistatic sensing. And if we have such multiple receivers, then it is called as multistatic sensing. So these are the three configurations of sensing. Now, when we talk about the designs, different designs in ISAC system, there are three types of designs. Whether we want to integrate uh, radar sensing into communication hardware, or if we want to integrate communication into radar hardware, based on that, we have three types of designs. One is communication centric, radar centric, and joint design. So, in the previous communication and radar coexistence, we looked into two aspects, that is, communication centric, radar centric, and now in ISAC, mostly the focus will be on joint design. Okay, so definitely the requirements, the objectives of communication and sensing will be contradicting to each other, which we will see. So that is where we need to. Definitely there is a trade-off. So we need to design a system such that we achieve without affecting the other system. Yeah. So when it comes to performance metrics, so sensing performance metrics, there are three things. One is detection, estimation, and recognition. In detection, it's basically about, it can be a binary or it can be multiple. Based on the noisy or observed signals, we need to determine what is the probability of detection of a target or what is the probability of a false alarm. Now, similarly, when about the estimation, estimation is basically about estimating some parameters. As I said before, it could be distance, it could be velocity, or it could be angle of the target. So we generally use mean square error or Kramer-Rao lower bound. So Kramer-Rao lower bound, definitely everyone would be knowing, which gives a lower bound on the variance of any unbiased estimator. So, so the variance of this parameter will be greater than or equal to inverse of the Fisher information. Now, when it comes to recognition, it's about what the sensed object is based on the noisy observation, right? So it's basically a classification task at the application layer. So if you look at the sensing performance tasks of the physical layer, the metrics that we usually look into are probability of detection, false alarm, mean square error, or Kramer-Rao bound. When we look at higher layer applications, then recognition is at the core of learning based. So when we talk about communication performance metrics, there are two things. One is efficiency and the other one is reliability. So efficiency is basically a measure of how much information is successfully delivered given some resource constraints, right? So we look at spectral efficiency, which is basically achievable rate measured in bits per second per hertz, or energy efficiency, which is bit per second per joule. And the other metrics could be coverage and maximum number of served users, so on. And reliability is basically to measure the ability of a communication to detect or correct erroneous information. So what we look into the metrics are generally outage probability or symbol error probability. Now, given these things, we'll just look at the two aspects. One is detection versus communication, the trade-off, and the other one is estimation versus communication. So for that, I have considered this passive sensing. The reason why it is called as passive sensing is because the detection of the target is done at the separated receiver, not done at the base station. So there are two types of channels here. First thing is there is a communication user and there is a passive sensing receiver, which is mainly used to detect the target. And there is a direct channel to the passive sensing receiver, and this is called as surveillance channel. The channel which gets reflected through the target is called as surveillance channel. Now, if you see in this figure, so I'm considering this as a reference. Now we need to design a power allocation because there is a communication signal waveform and there is a radar signal waveform and there is associated power. So we need to design this power allocation in such a way that we know that if I put more power to the communication waveform, definitely the communication rate will increase, but at the cost of reduced sensing performance. Now, on the other end, if you put more power to the sensing waveform, there will be a better detection, but reduced communication rate. Now, with this, if you look at the radar-centric optimization problem, the objective is to maximize the target detection probability, given the constraint that the rate for the communication user should be greater than or equal to a certain threshold. And another constraint will be the sum of the power that is used for the communication waveform and the radar waveform should be equal to the total available power budget. So now, how are we going to detect this? How are we going to find the detection probability? So for that, there are only two hypotheses. One, there may be target present, or the target is absent. So if you look at the direct channel signal is always present. If the target is absent, there will be only noise. On the other hypothesis, the direct signal is always present because it is processing the information for the communication user, which is heard by the passive sensing receiver as well. If there is a target present, then there will be a signal which gets reflected through the surveillance channel. Now, if you look at by correlating this reflected signal with the reference signal is basically the signal that is through the direct channel. So then you can determine whether the target is being present or not. Now that's how you can determine this detection, the probability of detection, which can be performed by using a GLRT method, that is generalized likelihood ratio test. Okay, so now this is there is a trade-off, right, in this detection versus communication. It's not just about detection. So while doing detection, you should also need to consider how much power you need to dedicate for the communication, such that achievable rate. It's the rate that can be achieved as per the requirement. Now, if you look at the communication estimation versus communication, I have taken another scenario here where there is a base station which is called as ISAC transceiver, which means there are transmitters and also receiving antenna elements, and there is a target, and let's say there are n users. Now the communication waveform, the waveform, let's not say communication waveform of the signal waveform, let's say a waveform which is broadcasted to serve these users, and also an echo which is received at the receiving antenna elements. Now our objective is to design a waveform itself such that it is able to serve the communication users, as well as you can also determine the presence of the target or maybe some parameters of the target using the same waveform. So with that objective, so the base station receives the echo of the signal. So let us not worry about this dimensions. If you want, I can tell you this is a simple multi-user MISO system. Yeah. So this is the echo that is heard, and this is the received signal for multi-user communication. Now, what I need to design is X. I need to design X such that using the echo signal at the receiver, I should be able to determine or estimate the parameters of the target. At the same time, I should be able to serve the communication user as well. So this G is basically, this represents the target response matrix. So if we try to formulate an optimization problem, it's basically to reduce the mean square error, that is the expectation of this G minus G hat. So this MLE denotes the maximum likelihood estimation. So I need to minimize this mean square error, where this X is what needs to be designed such that the constraint is what the Frobenius norm of this X should be less than or equal to L times the power budget, where L is the number of time instants. And there is one more constraint. This constraint is because of the communication. So this is a generalized expression. This is a communication utility function which is constrained by some quantity. This quantity, it could be based on per user SINR or some rate, or even it could be error rate. And this symbol denotes whether it can be greater than or equal to, or it can be less than or equal to. So if you look at the trade-off in sensing and communication, see, this non-line of sight was initially considered to be harmful to wireless systems, isn't it? So with the advent of this multi-antenna technology, this NLOS paths and fading effects were exploited to provide diversity and the degrees of freedom. But however, in sensing, not all paths are useful for sensing, because if there is no target present and if you are getting the reflections from paths, that could be basically cluttered. So there are some paths that will be useful for sensing, and there are some paths that will not be useful for sensing. So mostly sensing relies on the line of sight path between the sensor and the object. Yeah. So if you see in this figure, so there is a ISAC transceiver, there is a user and a target. This itself is the user and as well as the target, and there are non-line of sight paths. So the reflections from these clutters, they are called as non-line of sight paths. Now, so for communication, this non-line of sight paths are useful, whereas for sensing, this is not useful, right? So if you look at this, there is line of sight plus non-line of sight plus noise. This is the signal that is received at the vehicle from the communication user point of view. For communication user point of view, this non-line of sight paths will be useful. Okay. Now, if you look at the signal that is received, which we call it as an echo at the base station, we have the component that is reflected from the target, and we also have a component, multiple components that is reflected from the non-line of sight path, which we call it as clutter. Now, our objective is to design a waveform such that we can it should be carefully designed in order to allocate power and other resources where we'll be able to serve both the communication and the radar. So we have two things. One is receive SNR of the vehicle, which is basically this signal power divided by the variance. But for the radar, we look at this signal to clutter plus noise ratio. So this is the target component, and this is the clutter component. Yeah. So so recently we have done some work on this achievable on an average. What is the rate that can be achieved by using NOMA in an eyesight system? So NOMA basically we have used NOMA because this can be used as an efficient technique for interference management, and also we can use superposition coding at the transmitter, and by using successive interference cancellation at the receiver, the interference can be cancelled. Okay, so basically what we have done is we have considered a full duplex system where there are downlink two users, and there are two users in the uplink. We have applied NOMA in the downlink as well as we have applied NOMA in the uplink. There is an interference causing from the transmitter to sensing to the downlink users, and also there is an interference that is causing from the uplink users to the downlink users. Okay. So that means this U1 is causing interference to D1 and D2. U2 is also causing an interference to D1 and D2, and there is an interference that is getting reflected from the transmitter to the target to the downlink devices. Yeah. So we also have a loop interference here, because when it is transmitting, it is also receiving from the uplink devices. We also have considered this loop interference into account. All the channels are relay faded, and we have used NOMA transmission scheme for both the uplink and the downlink scenarios, while the superposition coding is used at the base station to transmit the information for both the downlink users D1 and D2, which is denoted respectively by X1 and X2. Yeah, so similarly we have the received signal at D1 and D2. These expressions are not so important, and we calculate the SINRs at D1 and D2. So basically D1 is the near user, so it first decodes the symbol of far user and removes it by applying successive interference cancellation to decode its own information, right? So now D2 is a far user, so D2 decodes its own information by treating X1 information as an interference, right? So in the uplink device, what happens is, since U1 is the near user, it first decodes the user 1 information, then cancels it to decode the far user information. Yeah. So basically what we have done is we have done the ergodic rate analysis, which is to characterize the performance of the considered system model. And yeah, so there are four user expressions, D1 and D2, downlink users, U1 and U2 are the uplink users. So if we look at this plot, basically we have considered three scenarios. The first one is to analyze the rate in the presence of the interference from the uplink communication users and a radar target. And the second scenario is by considering only the uplink communication users. And the third one is in the absence of a target and the interference. So if you look at the performance of this ergodic rate, In all the three cases, NOMA is considered to be better than the OMA scheme. And especially the performance of NOMA or OMA becomes better if you look at after P is greater than 10 dB. So one more observation was that NOMA with interference performs better with respect to orthogonal multiple access technique without interference. So this is the ergodic rate of downlink near user versus the transmit power P. And similarly, if we look at the ergodic rate of downlink far user versus P, until P equal to 15 dB, NOMA is better than OMA. And also, if the transmit power of the uplink communication user increases, the ergodic rate of D1 and D2 decreases. That is because that is also causing an interference to the users D1 and D2. So we are considering the co-channel interference. So that's the reason why if the transmit power of the uplink communication users increases, the ergodic rate of uplink near users U1 and U2. Yeah, so this is not near users, it should be uplink users U1 and U2 versus the powers. So basically what happens is if you increase power at the base station, definitely it increases the downlink performance, that is achievable rate at the D1 and D2 increases, and also the sensing performance improves. But it is also causing an interference to the received signal at the base station. So that means uplink rate decreases. And also since there is loop self-interference, there is a degradation in the rate achieved by the uplink communication users. So to conclude, basically we discussed about the fundamentals of two potential solutions of spectrum sharing. So one is the communication and radar coexistence, and the second one is integrated sensing and communications. In both the systems, so there is a trade-off that exists. While in the coexistence part, the main objective is to design interference management techniques. While for ISAC system, the objective is to design a waveform such that it can serve the purpose of both communication user and the radar sensing. And we discussed about one of our recent work, that is average achievable rate of downlink and uplink communication users in a NOMA assisted ISAC system. Yeah, so just some open, problems. If you look at the open problems, the first thing is waveform design. Basically, development of waveforms that efficiently support both radar and communication. So we have two things. One is non-overlap resource allocation. That is the fixed resource allocation, where it could be in terms of time, frequency, spatial, or code. And in the fully unified waveforms, we need to look at from the aspects of either, whether we are integrating communication purpose into the radar infrastructure, or if we are developing, so application of radar into the communication infrastructure. So based on that, we have sensing or communication sensing, or it could be joint design. And when it comes to beamforming techniques, so the important aspect is to design an active beamforming technique to steer the signal in the desired direction of, now not just to improve the performance of the communication, but now it is also to serve the radar sensor. Okay, and channel models, this is still not sure what are the good channel models that can successfully build an ISAC system, whether it is geometry-based channel models or ray tracing models. And also when it comes to information theory aspects, sensor information theory is still in its infancy stage. Well, when it comes to multiple access techniques for ISAC, definitely there is a scope whether the NOMA could be a potential enabler for the next generation, or even the rate splitting multiple access technique can also be employed in order to achieve, for example, weighted sum rate of the users. Yeah, the last slide, this is, so the usage of machine learning in ISAC system. So how are we going to determine this symbols in the presence of the radar as an interference? So probably we can employ the machine learning technique, or even to design this active and passive beamforming optimization for an IRS assisted system. And definitely design of this power allocation schemes. optimal power allocation schemes for radar and communication coexistence or ISAC system. Yeah, so these are some of the important references, but however, I have put the references in the slides as well. So thank you.
Long live India and France friendship.